This is the second in a series of 3 webinars that HUD is sponsoring, with the next one scheduled for July 27th. The first webinar was recorded in June and will be posted. I'll get into that a little bit more detail. Next slide, please. This slide just summarizes the first webinar, and we will be making that available. We're going to set up a site on HUD Exchange, and that these webinars will be archived and posted on HUD Exchange site, along with other guidance materials. Some of the guidance we're developing will highlight some of the main points of the national, the Radon consensus standards, the ANSI ARST standards that have been developed with EPA assistance. You'll hear more about those in the presentations today, but we will be posting guidance that summarizes some of the main points from the standards, as well as other materials. So today we're talking about mitigating high radon levels in single and multifamily homes. And if you go back to that last slide, please, Jennifer. And then the third webinar scheduled for the end of July, July 27th, we'll be talking about planning and implementing radon risk reduction. So how do you find qualified professionals? How do you plan to test and mitigate radon on your property, especially if you can't do it all at once? And we know that many of you have to phase it over time. Next, please. So today, we're going to have our first speaker, Dave Kaptarowski. Will be talking, he'll be reviewing radon basics and going over testing and mitigating radon in single family homes. And then the second speaker today is Kyle Hoyleman. If you joined us in the first webinar, you'll recognize Kyle's name. He presented in the first webinar as well. Kyle will talk about testing and mitigation in multifamily dwellings. So let me introduce our 2 speakers now and get that out of the way. Dave Kaptarowski goes by Dave K. Dave is Vice President and co-founder of Spruce Environmental Technologies Incorporated. He has over 30 years of experience in radon testing, mitigation, mitigation equipment manufacture, and laboratory operations. Dave is a board member and treasurer of the American Association of Radon Scientists and Technologists, or ARST, and he's chair of the ANSI ARST Soil Gas Mitigation Standard and CCAH New Construction Radon Standard, as well as a participant in several other ANSI ARST standard committees. The next speaker is Kyle Hoyleman. Kyle co-founded Protect Environmental in Louisville, Kentucky in 2005, where he currently serves as its managing partner. He's led the company in the completion of more than 5,900 radon and chemical vapor intrusion projects across the country since its founding. Kyle currently serves on the EPA Vapor Intrusion Science Advisory Committee, the National Radon Action Plan Leadership Team, and chairs the Standards Management Committee developing ANSI standards for radon and chemical vapor intrusion testing and mitigation. He was elected to president of ARST in 2020 and serves on the board of directors. So as you see, we have very experienced and knowledgeable presenters today. I think you will agree after you see the presentations. So just wanted to go over a few housekeeping items highlighted on the next slide. If you have any questions during the presentations, please put them into use the Q&A feature to submit your questions. We'll wait to the end of both presentations to answer questions. if you have any issues, like technical issues with the webinar, you can add them to put them into the chat feature, and we'll try to resolve those. No guarantee, of course, if it's at your end, there won't be anything we can do about it. Also, I wanted to mention that we have with us today Justin Gray. He's part of our team, planning team for these webinars. Justin's an environmental compliance officer with HUD's Office of Public and Indian Housing, and he'll be available to help answer questions at the end of the presentations today as well. So, so with that, let's continue. This is just contact information for our staff today, our presenters, myself and Justin. And with that, we'll start off with Dave Kay's presentation on radon, some radon basics, and a look at single-family testing and mitigation. Dave?
Thank you, Peter. Can someone confirm that they can see my presentation?
Yes, it looks good, Dave.
Okay, thank you. And welcome, everybody. I'm going to go through today, first providing a little background, some of the basics on radon and health effects of radon. And then we're going to take a look at testing and mitigation in single-family homes, in particular, the two ANSI standards, which govern both testing and mitigation. Now, a single-family home is defined by the standards as being no more than 3 stories in height and no more than 4 connected homes on a contiguous foundation. So that will be the scope of what our discussion will be here today. So just a little background on radon. Radon is a known human carcinogen. Okay, so it's not a suspected carcinogen. We know that from both minor studies as well as many epidemiology studies dealing with the residential environment that radon causes lung cancer and is the #2 cause of lung cancer in this country. It's a naturally occurring radioactive gas. I'll explain a little bit about radioactivity so you get an understanding for that, including what a 3.8-day half-life means that relates to a radioactive property. You cannot see it, smell it, or taste radon. So radioactivity. Everybody remembers from their 5th grade science class. This is a model of an atom where you have a nucleus and you have protons and neutrons in the nucleus, and it's surrounded by electrons. Radioactivity simply means that the radon is unstable and it will spontaneously change to try to get to a more stable state. And when it does that, it will release various types of energy. And that can be in the form of an alpha particle, which means that 2 neutrons and 2 protons will get ejected from the nucleus. And so that's a very massive, slow-moving particle that gets ejected. A beta particle is actually an electron, and gamma is a form of radiation. So not to get too philosophical, but the meaning of half-life, what that simply means is you see the box here on the left, and if it was completely sealed so that nothing could get in and nothing could get out, but we had 12 radon atoms in that box. And if we waited 3.82 days, we would have exactly, well, we would have 6 radon atoms that would be left. And in fact, if we waited another 3.82 days, there would be 3 radon atoms left in the sealed box. So you may ask yourself, well, what's the big deal if radon disappears like that? If we just close the house up for a couple of weeks, then radon can go away. But the problem is that radon comes from radium, which in fact has a half-life of 1,600 years. So you'd have to close the house up for a very, very long time. This chart here, I don't want you to look too much at the details, but what's important is that you understand that when radon goes through its radioactive decay, you can see here that radon 222 will decay into polonium 218. And it does that, it ejects an alpha particle. Polonium 218 also will eject an alpha particle, as well as you see over here, polonium 214 will eject an alpha particle. And then eventually the radon will decay to lead 210, which is relatively stable and has a half-life of 19 years. But the polonium atoms that give off alpha particles are important when you're looking at the health effects of radon. So alpha radiation, if we look at the types of radiation that come out, but alpha radiation is the most destructive to biological tissue. That's because it's very massive and it's very slow moving, and it can interact with the body and cause a lot of damage. But an alpha particle can be stopped by a sheet of paper, and it can also be stopped by the dead layer of skin that's on the outside of your body. And in fact, an alpha particle can't travel more than an inch in air. It will collide with so many other molecules that are in the air that it will stop within an inch. So if that's the case, why is it that that the alpha particle is detrimental to your health? And if we take a look at it from the lung cancer risk, when you inhale radon, you will in fact exhale the radon. Because of its long half-life, it will not decay inside your lung. But if we look at the situation where we inhale not just the radon, but also the polonium that was in the decay chain, well, the radon will exhale, but the polonium is adhered to the mucus layer of your lung. And so when it decays radioactively, it does so where the alpha particles don't have to travel an inch to interact with the bronchial tissue inside the lung. And there's no dead layer of skin inside your lungs. And so there's because of that proximity, there's a very good chance of causing actually cellular damage that can lead to lung cancer. So just a little bit of a summary here. When you inhale, not only radon, but radon daughter products are inhaled. The radon you'll breathe out, but the RDP, the radon daughter products, can stick to your lungs. And so if those alpha particles that it emits will strike the DNA inside a cell, this can cause a mutation that can lead to lung cancer. And the very insidious thing about lung cancer is that by the time you and your doctor figure out what's going on, it's generally that the lung cancer has progressed until stage 4, and there is no stage 5. And so generally you have 6 months to get your affairs in order, and it's a very lethal cancer. If we look at in the US, radon is responsible for more than 21,000 deaths each year. And you can put that, and these are just comparative examples as to other risks that you may face in the home or driving with drunk drivers. But carbon monoxide, which is something that you may have to deal with relative to building codes and putting in carbon monoxide detectors, is responsible for less than 500 deaths a year. However, they tend to be much more dramatic when a family of 5 gets carried out of a home because of a problem caused by carbon monoxide. It usually makes the 6 o'clock news. In order to have a radon problem in a home, you need to have a source of radon and a driving force to move the radon gas, as well as an entry way into the home to have an actual radon problem inside the structure. So if we take a look at radon and soil, which is the #1 source of radon in a residential environment, it comes from soil. That's dependent upon how much radium is in the soil, how big those particles are, how permeable or what the porosity of that soil is, and then the strength of the forces that are available that can move it through the soil. So that's the discussion relative to source. We look at the driving forces that are available in the home. First driving force is diffusion. So if we had someone that was in a room and started to peel a banana, that person would smell the banana right away very strongly, but eventually that smell would permeate the entire room, and so everyone in that room would be able to smell the banana. So the radon would move in a similar manner. It moves from a high concentration to a low concentration through diffusion. Exhaust ventilation also represents a driving force in a home. If you turn on your clothes dryer, air is exhausted outside of the home. Similarly for your kitchen hood, as well as your bathroom vent. And so when air is blown out of the home, it has to be replaced. And so some of that will be replaced by drawing in soil gas, and that becomes a driving force to bring radon in. Thermal bypass simply talks about gaps that exist in a structure as it's built. They're not really airtight, and so it can move around various structures in the built environment. But the most important driving force is actually called the stack effect. And essentially, hot air rises. So as we either heat during the winter, so that because it's cold outside, or if we're picking up solar gain from the sun, that causes the hot air to rise. And as it rises to the top of the building, it will find its way out of the building. And this creates a negative pressure that again will draw in radon and other soil gases. In terms of pathways, there are a number of pathways that exist in the built environment for radon to enter. If you have a private well, okay, the well water can in fact be a path. If the radon is in the water and you use it in the shower, that becomes a pathway. But by far the most important source for radon in a home is the soil. And so gaps in the foundation, that's caused by cracks, plumbing penetrations, or water water drainage features such as a sump pump become pathways that allow the radon to enter. But every home is different. So we need to understand that even if two homes were built by the same builder right next to each other, it's very dependent upon the proximity of the source, okay, which would mean radium-laden soils that exist. Are they close to the home or are they farther away? What's the material, the native soil that's there? Is it something that's sandy or bony rock so that air and radon gas can move very easily? Or is it clay, which is very dense and difficult to transport? So all those things, along with the natural building ventilation rate as to how tight the building is built, and openings that provide the radon to enter the home, all mean that two houses right next to each other can have very different radon results. And the only way to know for sure whether you have a radon problem is to measure for radon. So the American Association of Radon Scientists and Technologists, we have a consensus, an ANSI consensus standard consortium. And I think we have about 10 standards that are currently published. I'm going to spend a little bit of time talking today about the testing standard, as well as the mitigation standard, which is installing a system that would actually control and remove radon. But the measurement standard for radon in homes establishes rules that are used by professionals for putting a house under a set of conditions to make sure that you have consistency in your test results. Now, that doesn't mean that if you do a test in July that you will get an identical test result in September, okay? Because there are variations that occur seasonally. There's variations that occur daily relative to radon levels. But by putting the house under a certain set of conditions, it allows it to be at least somewhat more consistent. When we're talking about single family homes, these are the types of test devices that you could encounter, meaning some of these require like a liquid scintillation, an alpha track, and an activated charcoal test kit. They're exposed in the home and then sent to a laboratory for analysis. Other types of devices, such as an electret chamber or a continuous monitor, can be analyzed on site. And so you can get a result more quickly than you can if you have to transact for the devices and send them back to the laboratory. The test standards, there's a number of do's, okay, things that you are very important relative to getting a consistent result. Most important of which is closed house conditions. Okay, the house should be put under a closed house, which means all the doors and windows are closed. Now, it doesn't mean that you can't go in and out of the building. You can do that, your normal entry and exit. But for at least 12 hours before the test and during the entire test period, you would want to maintain the door and window closures. Now, if you're doing a long-term test, which is greater than 90 days, then those closed house conditions do not need to be met. The test has to last for a minimum of 48 hours. If someone does a grab sample test that they do over 5 minutes or 20 minutes or something, that's not a valid test according to the testing protocols. So you would have to be a minimum of 2 days. It could go out to 5 days. Most short-term tests are 2 days, and that's the the best result. Test location should be in the lowest level that could be occupied. In terms of the properties that you're dealing with that are single family, I think you have rather small footprints. You're dealing with either front room or a bedroom. That would be obviously be your occupied levels. In a single family home, you may have a basement, and that would be considered an area that could be occupied, and that would be where the test would be conducted. Keep the test off the floor, a minimum of 20 inches. In larger buildings, you would want to have multiple tests. And so for every 2,000 square feet, you would want to have at least one test. And if there are different HVAC systems, they should be tested independently. If the property is unoccupied and has been unoccupied for a while, you need to make sure that it's heated and cooled and put it into a conditioned environment to get a consistent radon result. And if you're doing a post-mitigation test, which means after the home has been corrected for a problem, you give the system at least 24 hours before starting the test. As important as do's for testing, there are also don'ts. You shouldn't test inside the kitchen or a bath because of the high humidity that is in those areas. That can interfere with the test. And you really want to sample and get an environment that represents the test occupying the breathing zone of the home. And so you wouldn't test inside a closet or put a test kit in a sump basin or a crawl space because people don't live in those areas. Keep it away from heating sources and also drafts, which could be from the HVAC system or within 3 feet of exterior doors or windows. When a test is completed, the Radon Professional should provide you with a written report. And that written report will give you your test result. The current EPA action level is 4, and this represents picocuries per liter. So it's a measure of radioactivity in a volume of air, in this case, a liter. Nobody knows how big a liter is, but think of a 2-liter bottle of Coke. That would be 2 liters. And so if you had 4.4 disintegrations per minute in a 2-liter bottle of Coke, that would equal 1 picocurie per liter. So if you get a result that is above 4, okay, this would be where you would be considering mitigation to reduce the radon levels. Just a couple of other things that you could come across. The World Health Organization does have a reference level, and this is a different unit, which is 100 becquerels per cubic meter, but that translates to 2.7 picocuries per liter, so slightly less than the US action level of 2.7. You may come across that from time to time. And you should be aware that the EPA does recommend fixing levels between 2 picocuries and 4 picocuries per liter. So if we take a look at the ANSI ARS mitigation standard, the SGM mitigation standard, this again provides rules for use by radon professionals to safely and effectively install a radon removal system in a single family home. And the best available technology for radon removal is active soil depressurization, or ASD. This can be up to 99% effective in reducing radon levels. You can never reduce the radon levels in the home to lower than what the outdoor air radon levels are. But because the house is under negative pressure, it tends to pull in soil gas, and the intent and the operation of an ASD system is to remove the radon which is directly beneath the home so that it can be exhausted above the roof of the home and evacuated before it has a chance to enter the home. According to standard, every building that's going to have an ASD system installed does require a radon professional to come on site prior to actually installing that system. That could potentially happen at the day that the system is installed, but certainly there needs to be a qualified radon person there to make sure the design layout is such. And in general, it should be done before quotations are provided and work begins. As property managers, and you're working with structures where these are not homeowners, but they are occupants of the building, they would require notice, okay, that this work was going to be conducted. So the contractor would be working through you to make sure that everyone that's in one of these buildings knows what's going on, knows what the potential health hazards are, and what are being materials that are being used to install the radon system. So this is a schematic of an ASD, an active soil depressurization system. You can see down here, soil gas collection plenum. As I said, the main use of that ASD system is to remove the radon that exists below the home. And it connects up through system piping, which can route any number of different ways. But here we see it going through the house and then goes up to a fan, which is mounted up in the attic. And this fan has to run continuously. And its purpose is to, again, to evacuate the radon out of that soil that's below the house. All the piping that you see here that's below the fan is under negative pressure. So if there were to be a leak, then in fact air would get pulled into the system and you wouldn't be sending radon. If it were positively pressured, you'd be sending radon into the home. And then it's exhausted above the roof so that it can dissipate into the atmosphere. These are some of the more other visible parts of an ASD system. It should be properly labeled, meaning that there's a main system label that provides information about the contractor and when it was installed. Piping and other aspects that are important to operation of the system should also receive a label so that, 20 years from now, someone can understand that it's not part of the plumbing, but is in fact part of a radon system. Other visible aspects of it, a pressure gauge. This pressure gauge, which is called a U-tube manometer, gets installed in a place on the pipe, and it measures the pressure that is being developed by the fan. That can be useful information to tell you if something's changed on the fan, but all too often the pressure gauge itself is not understood well enough to know whether you're having an actual system failure or not. So the standard does require an audible alarm. And so if pressure is lost inside the system, it will provide notification, an audible notification to the occupants. Sealing is also a very important part of ASD installation. You want to try to close off radon entry points, and if that may be on a foundation where you have a concrete wall that meets a concrete floor, there's a crack, and that would be sealed. Plumbing penetrations are also an area that can be open to the soil and allow radon to come in. And again, groundwater control systems such as a sump pump would need to get closed off and sealed as tightly as possible to keep radon from coming in. In terms of allowable locations for the fan, the primary concern here is to prevent leakage into the living space. And so the fan could be mounted in an attic. If there's an adjoining garage attached, it can mount in the loft of the garage, or outside of the home. And so these are the allowable fan locations. In terms of exhaust locations, there are some rules relative to where that can get exhausted. It generally has to be above the roof of the home, a minimum of 10 feet above the ground, and away certain distances from doors and windows so that it doesn't have a chance to re-enter the home as it comes out of the exhaust. If the SGM system, the ASD system is installed, again, every system needs to be tested, but you would wait a minimum of 24 hours before testing a system that is installed. Other thing that's required by the ANSI R standard is a maintenance and monitoring plan. And this would just be a document that explains how the system works, explains how fan monitors, what their purposes are and how they work, recommends testing and retesting every couple of years, and would provide information for the contractor. And that's it. My contact information, dave@spruce.com, if you had something to contact me directly. If you're interested in the ANSI R standards, you can go to standards.ars.org, and they are available and viewable here as a flip book. And if you're looking for Radon Professionals, there are two organizations, national organizations. This is the National Radon Proficiency Program, which is affiliated with ARST. And there's the National Radon Safety Board also. And in addition to that, there are some 20 states that have potential licensing requirements. Some of them just refer back to these programs, the NRPP or the NRSB. And in general, if someone is listed, say on the NRPP organization, and they're located in Ohio. Ohio is a licensing state. They would have to also be licensed in Ohio. So that's it. And Peter, I'll toss it back to you, and we'll be taking questions at the end.
Okay, thanks very much, Dave. I appreciate that. Thanks for your excellent presentation. We'll now turn it over to Kyle to continue the discussion, this time with a focus on multifamily buildings. And a reminder to use the Q&A function if you have any questions. Thank you.
All right, thanks, Peter. Just a quick check here. Does everybody have my screen?
Looks good.
All right, very good. Good afternoon, and I'm going to just go ahead and dive right into it. My name is Kyle Hoyleman. I'm president of ARST and also a contractor based out of Louisville, Kentucky. A lot of the information that we're going to talk through, Dave Kay has covered in his discussion, and we're just going to expand on certain aspects as they would apply to multifamily housing units with more advanced structures. The first slide that I'm going to put up is just one that Dave has already shown, and this is showing the three components. You have to have a source, you have to have a driving force, and you have to have a pathway, a preferential pathway into the building in order to really see that, that radon problem that we're talking about. As Dave mentioned, there are different contributing sources, and the most prevalent is going to be radon from soil, and that's really the focus of our presentation. So when we talk about mitigation, we're talking about the most common mitigation being active soil depressurization and how that would apply to occupant exposure or mitigating occupant exposure in multifamily buildings from soil gas. You can see here that there are some other sources, radon and groundwater. When you have private well supplies, things of that nature, it's not uncommon to see radon off-gassing from the water supply, which creates a problem. The northeastern part of the United States is probably the most prevalent area for radon from water. The other contributing source is emanation, and the southeastern part of the country, Florida, you get down into Puerto Rico where it's the building style, it's the limestone content and the concrete that actually emanates. And when you couple that with more energy efficient building practices, lower ventilation rates, now you have the potential for radon exposure that's caused by the building material source itself. So the basics are the same on the single family as well as the multi-family housing side, as far as where radon comes from, how it makes its way into the structure, and the forces that cause it to be there. Foundation type. Primarily, there are three main foundation types in the United States. There's the basement, which is below grade slab type foundation. There's the slab on grade foundation, and then there's crawl space foundation. And as we looked at that from a single family conversation that Dave has just gone through, these are pretty straightforward, as you see here on your screen. But what happens when radon presents itself in more significant structures with independent HVAC systems and whatnot? And that's what we're going to get into. So for those of you who joined the session last month, this slide we talked about, and that is a more advanced structure. This project just happens to be in Nashville, Tennessee. You can see that it's made up of a lot of individual residential units. And if you think of each of these as its own independent living area, and it just happens to be under the same roof. So it's not uncommon to see different HVAC settings right next to one another. It's not uncommon to see preferential pathways into one unit that could not be present in another unit. And so if you think of neighborhoods, and Dave mentioned the only way to know if a radon problem exists in a subdivision between you and your neighbor's home that may be right next to it is to test. It's the same concept within the building envelope. The only way to know if a radon problem exists is to fully characterize the building. Otherwise, we wouldn't know that we have 18s and 27s in these three units, and directly across the hallway, you have a unit that's a 2.2. Very similar if you looked at these as just separate houses. This would not be uncommon to see this within a neighborhood. So what causes that? And we talked briefly the last time about building structure. So here are those three units that were on that hallway. You can see here that these have continuous footers. Continuous footers are concrete that more or less subdivide the sub-foundation area of the building. And you could have a pathway into this area that doesn't exist here. You could also have a usage of this area that's different. So for example, Mr. Smith may live here and he may keep his HVAC system set at 85 degrees year round. Next door, Mrs. Smith lives here and she keeps hers at 60. So when you go back and you talk about the thermal stack effect, most likely the stack effect is going to be greater here, just because of the individual way that the environment's used. These are where these continuous footers go. And so these would be typically 11, 14-inch wide grade beams, continuous concrete footers, and that further complicates how we mitigate these structures. So we talked last month about how do we characterize the structure to determine if a problem exists. This month, we're going to talk about a problem does exist. How do we mitigate the occupant exposure to radon in that scenario? Advanced foundation types. This is a different type of foundation. So we just looked at the last slide being that Nashville structure. Well, here's a different type of structure. This is called a post-tension foundation type. And all of these blue areas, these are tendons, and more or less they're under great tension. So you don't want to drill into these. It can greatly impact the structure. What you're going to see here is a waffle looking type of structure where it's concrete. Concrete is poured, the tendons are inside of the concrete, and this type of structure is typically used in areas where we want a little more stability or flexibility in how the building reacts to things like seismic events, things like that. These structures are pretty typical in the southeastern part of the country, as well as Texas and other areas, and they're becoming more prevalent through the country. From a mitigation standpoint, these structures create an enormous challenge in that each one of these are really separate concrete areas underneath the building. And if you have a pathway in one area, the pathway could not exist or in the area next to it. That's how variable some of this localized radon preferential pathways into the building becomes. So a lot on the multifamily side, there's a lot more diagnostic and pilot testing work on the front end to make sure that the design is correct so that the system operates and mitigates the occupant exposure on the back end. Unlike a single family residential building, you're typically not going to see heavy grade beam use or continuous footers under those buildings. In most multifamily environments, you are going to run into these types of scenarios. Another scenario, this is just a different look at how those concrete continuous footers work under a building. So you can see here that we've effectively segmented different areas of this building into different sub-foundation areas. And then now the radon could potentially just be going through these pathways from area to area. And from a mitigation standpoint, that also creates a challenge because instead of pulling air freely or inducing that vacuum freely through the building that Dave K talked about, now we're limited in how we might make that happen. So it's a more just a complex version of a single family building, but the way that we go at diagnosing and laying out and designing that system is much different. So where do you start? You start with making sure that you have the right folks on your team. The standard identifies the qualified radon professional as credentialed by one of the two national proficiency programs. Dave K mentioned those, and you have the links now. And then also there are 20 licensing states, licensure and or certification. So you would want someone that's experienced with multifamily buildings. It's a lot different to mitigate a multifamily structure, both from a short-term cost of installation, but more importantly, from a long-term stewardship cost. And we'll talk some more about that. But you want to make sure that your qualified radon professional has experience. That person would be the one that's reviewing the design, reviewing the field work, making sure and supervising the installation of the system, as well as all other aspects of subcontract work and different things, electricians, roofing contractors. And then ultimately this person becomes responsible for your mitigation system, routine and non-routine maintenance, as well as your ongoing monitoring. I did want to note that the Environmental Law Institute maintains a database, and right now there are 40 laws or 40 states with radon laws on the books, and 20 of those do require licensure and or certification with standards, and you have the link there for future reference. The mitigation standard for multifamily buildings is MF 2018, and there is an updated revision. The standard provides the guidance for the qualified contractor we just talked through. The health and safety planning. We're using, there are VOCs in some of the materials that we use in sealing, different things like that. Plus radon is a Class A human carcinogen. So just as we're mitigating the occupant exposure in the building to the resident, we want to make sure that the worker safety is taken into consideration as well. A lot of communication. You have buildings full of residents. You show up and you start drilling into things and going into units and providing access, notifications and whatnot. Folks want to know what's going on. They're being inconvenienced, but they're also, they need to know what the process is. And we'll talk a little more about that. Always go through a system design. And we're going to show some examples of that, as well as your installation. When you're done, the guidance, the standard provides guidance for what you're clearing. You're not clearing an individual unit within the building. You're clearing the units within the building, because we've potentially changed the pressure dynamics of the building. And so maybe where that 2.2 was in that Nashville project that we looked at, just changing things around could present a problem there. And so you're always making sure that you're clearing the structure as a whole, not just a certain part of the structure once you've done mitigation. The end result is we now have a system in place. We need to do two things from a long-term stewardship standpoint. Number one, make sure that the mitigation systems are continuing to function as designed. And number two, verify or confirm that radon concentrations within the building remain below the EPA action level. And then one thing I do want to note, and this has come up just recently with some other HUD discussions, is chemical vapor intrusion. And I think Nelson has done some presentation work. He's one of the resident experts within HUD as far as chemical vapor intrusion. But I do want to just point out that these standards are also standards that are applicable to chemical vapor intrusion into the building. Dave mentioned that the standards are available online. Those standards are available at standards.arch.org. You just scroll down, and if you wanted the multifamily standard building, for example, you just view that standard. It pops it up in a flip book, and you can easily go through, go into the instructions. Hey, I want to know what the health and safety requirements are, and basically go right to that page. This access is complimentary, and then if you do determine that you need print or PDF copies, you have the ability to do that through the standards link. So if you have questions about single family, it's in here, multifamily, schools and large buildings, your new construction, and then your quality assurance, which we spoke about last session. From a communication standpoint, there's several different stakeholder groups that need to be in the loop. Number one is the client and the management team. So here's an example of that communication that may go out to that team. And notice here that we're talking about drilling into concrete floors and application of sealants, different things like that. And what phase of this? Are we in the design and investigation phase? Are we actually installing systems or maintenance? And what are the impacted areas? The second communication is from this stakeholder team to the on-site, the property management, excuse me, maintenance supervising staff, things like that, and it's reiterating where we're at in the phase, as well as what we're going to be doing with this phase. And then probably the most important communication is that goes out to the resident. So here's an example of what that communication might look like. It's directing them to an EPA resource if they have specific questions about radon and how that might be impacting them. And again, just keeping everything common. We're here to investigate, we're here to install a system, we're here to conduct maintenance. And what are we actually doing? How is this going to impact you as a resident? And then I just note here that we really need to make sure that we're advising the occupants that we're using caulk and sealant. Sometimes the polyurethane that's used, it off gases. We try to use low VOC, but it stinks and it can make people nauseous and headaches and things like that. So we just want to be very upfront with what's going on. We want to let them know that the material safety data sheets are available and direct them where to get that information. So setting up the project to a successful project really starts with making sure that we have good, open, transparent communication between all of the stakeholder groups. Once we've done that, we need to determine now, and this would be the investigation side, what are we actually doing? We know that there's a radon problem in this building. Dave K mentioned active soil depressurization being the most common. That's what we're focused on today. So if we look at this flow chart, which is in the standard, it's going to walk through. I'm not going to spend much time here. It's here as a reference in the slide if you want to go back through that. But 9.910 times out of 10, you're going to arrive at proceed with active soil depressurization. And so from that standpoint, what are we really looking at with with the design itself? There's three main components. The first thing we want to do is review the documentation. What are the radon concentrations? Where are the units at that are impacted? Anything like that. Are there any known hazards in the buildings? From a public housing standpoint, you have that information. You know if there's lead-based paint, you know if there's asbestos containing materials, and we have to take that into consideration as part of our overall mitigation project, because we are potentially coring into areas that could have known hazards. The building plans, the operation specifications for the mechanicals, all that's really reviewed prior to putting boots on the ground. The second step would also be quasi off-site, but mostly on-site. And that's what type of foundation are we looking at? What are the HVAC specifications? Are there any other mechanical systems that could impact driving force? The extraction point, where are we going to install our soil gas collection plenum? How are we going to route the vent system? Is it going to be to the interior of the building or the exterior of the building? And then another big item is the electrical. These systems don't consume a lot of power, but they do consume power, and figure somewhere between $50 to $100 on average per system per year for power. We have to figure that out for the residents. Some states have prohibitions against tying directly into resident paid, and we may be talking about a credit. If there's not a house meter for common power throughout the building, that needs to be taken into consideration, and that needs to all be really mapped out on the front end of this process so that we're not running into challenges later. And then the other thing that we're doing is, what do we need to do to confirm that our system design is actually going to work on the front end, that we're not trying to pull air through continuous footers that we weren't aware were located there, and that's impacting our driving force and our preferential pathway. And we're going to do that through our diagnostic investigation. And then we're going to talk a little bit about collateral mitigation. We're going to talk briefly about it, but it's a very large driver from the standpoint of economics in buildings, both short-term and long-term. So the pilot test. You can see here a couple tools. These tools are mostly handmade. There's a gate valve here, a pressure monitor or a pressure gauge. And then we've cored through the foundation of this building. We've installed PVC or inserted PVC piping through the other side of the foundation. And this then is hooked up, this pilot test rig is hooked up to a vacuum system. So why do we do this? Because there are literally hundreds of different scenarios that could exist and hundreds of different solutions. We have the ability to emulate the majority of those through this one system. So from a pilot testing standpoint, ASD really relies on three things: pressure, resistance, and vacuum. How much pressure does the fan have to apply against the material that's under the building, that resistance? And that material could be clay. It could be crushed stone. It could be compacted crushed stone. It could be large 57. So it could be native soil. So we need to understand what's under the building and how our system is going to need to operate to overcome that resistance to induce enough vacuum to maintain the negative pressure differential with reference to indoor air that Dave mentioned. We do that through this system that's up here. And then this little guy here is handheld. And this is what we're using to measure that sensitive induced vacuum. It's a micromanometer. Our design benchmark, for example, is negative 10,000ths water column inch. And these gauges are what we use to determine if we're meeting that benchmark. More or less, once we've done that, we're looking at a radius of influence. So if I induce or my pressure here, or apply my pressure here to this building, how much is my radius of impact that I can look at to achieve collateral mitigation? And collateral mitigation is nothing more than the ability to design a system that has the mitigation effect over multiple units. So instead of putting one system in every single unit, we look at the building structure, determine if we can achieve collateral mitigation through this process that we're looking at right now. And that tells us where the systems need to be located, how many systems need to be installed. And then we've done our building evaluation now, so we know where they're going, how are we going to discharge them, where are the fan locations going to be, where are they going to discharge, interior, exterior, and finally, what's the electrical configuration. One thing, we have the Gpr Utility Clearance note here. Gpr is ground penetrating radar. That really needs to be done. If you go back and think about those post-tension buildings, you wouldn't want to just go in and start drilling. You wouldn't want to drill in or core into any building without proper clearance. Sometimes you're bringing a ground penetrating radar on site. Other times you're just merely contacting the before you dig type folks to have that cleared. So here's an example of what that radius of influence looks like. So this is in a single unit, but you can see here is where I put my soil gas collection system. I put my pilot rig in, and then I'm turning this vac on, and I'm measuring how far from here to here, and what kind of result do I get. So I have an extraction point. I gated my valve down to 3.5 inches, and based on that pressure, here are my readings from here to here at 3.5 inches. So I had negative 940 thousandths. That's much greater than negative 10 thousandths. I'm looking here, and what I'm starting to build is that radius that we talked about. What's my radius of influence? If I put a system that's capable of 3.5 inches water column in, will it communicate. And that's important because here are 4 different sets of fan curves, and you can see there's this is one manufacturer, and here's 17 different fans or 12 different fans. And notice here's my pressure. So these are rated for pressure, and then here's my vacuum or my flow at that pressure. So as I start looking at this, I'm able to say, yeah, first of all, I can achieve whatever my design benchmark is, in this instance, negative 10 thousandths. What's going to be the best fan? Is it going to be a GP fan at 4 inches? Is it going to be an HS fan? These fans go all the way up to 48 inches. And that's how we're using those fan curves to determine our system design. Now, when we talk about collateral, here's just a little different look. So I've now gone in and I've installed this. Here's my collection. Now I'm starting to build that radius out. Here are my numbers. Hey, I'm above 10 everywhere. I've got 9 units here, however many are here. Based on this radius that I've calculated, I now know that in order to mitigate this number of units within this building, I need to put 2 systems in. And this could also be a hybrid where I had just 2 extraction points connected to one system. Here's my building evaluation and everything goes in. So there's a good example of collateral mitigation. In order to do this, if I would have had, 3, 4, 5, 6, 7, 8, plus some other areas, I could have had a contractor tell me, well, you have to put 8 systems in, but by taking a step back, we're able to determine that we could put 2 systems in and effectively mitigate occupant exposure in 8 areas. Options. There are a variety of options to connect your system to the soil gas plenum. So here's probably the most common in existing buildings. We're just going to excavate a pit and install pipe. If there's a drain tile, perimeter drain tile, you can actually pull into that. That creates less resistance. If it's a crawl space, there has to be a vapor retarder installed so that we can create our collection plenum and pull that way. Sump pumps, and in some instances, you may even be depressurizing hollow block walls. These act as chimneys in some instances, especially if they're not capped here. And a lot of times the radon will actually come up through the hollow cell and into the built environment that way. So you're taking and you're factoring in these considerations as part of your design. Routing options. Dave K talked about interior versus exterior. So there's our two options that we're looking at. And then discharge options, and you've seen these as well. The standard is pretty much applicable to both single family and multifamily. 10 feet above the grade, above the roof edge by a foot, 10 feet away from openings into the structure if you're in 4 feet above them. Yeah, just that guidance on how that design needs to be pulled together in order to meet the requirements of the standard. And the importance here is to make sure that we're not re-entraining this radioactive material back into the building by not discharging it properly. So all of that comes together into a final design. And here's what the final design ended up looking like for that building. There's our 2 extraction points or our suction points that we put in. And here's what we actually are installing. Fire collars going in, the exhaust, the blowers actually in the attic, the fan is in the attic. Here's everything that's mapped out, and this goes into the bigger specification. So our end product here is, before we've ever done anything from a mitigation standpoint, we've done all of this. We now know that the extraction points are going to be here and here. We know that the vent locations are going straight up from each of these extraction points, and here are the components of that. It's going to discharge through the interior of the building, through the roof. The location is here. The fan specifications are here off of that curve that we've looked at. Ceiling, do we have exposed floor to wall joints that we can access? Electrical, we've talked through that. And then this also pulls in your worker health and safety, as well as your post-mitigation testing and your ongoing or your long-term stewardship for ongoing operation and maintenance. So all of that is done prior to ever showing up at the site with a construction crew. And here's kind of a few examples of finished product. So this project, I believe, was in Maryland. You can see that this is an exterior system. So you have a bore through the foundation below grade. It's pulling out. It's mounted under a security cover. Here's your electrical disconnect switch, and it's pulling off of house power. You have your monitor on the outside of the building. This monitor has to be specially configured because it is an exterior, not on the interior. That's covered. We have lots of little folks running around these communities, so we don't want them to be able to directly manipulate or harm the system in any way. And then here's our bracketing, and here's our discharge point. So we're clear here, we're clear here, and that's a typical exterior system that you would see in a multifamily environment. By the same token, there are interior systems aesthetically. That's really the only difference. They perform the same on the interior, the exterior. It's aesthetics that we're looking for. So here's, I believe this was in a closet, just trimmed out. Your fire collars have to be installed with these. Here's your monitor that's accessible. Here's a blower or fan that's mounted in the attic. And you can see here's the electrical service disconnect. That has to be within 6 feet of the location of your fan so that it can just simply be plugged in to operate the fan. And then there's an example of a roof penetration to your discharge point. So that's that's an exterior. This is an interior configuration, and all of this at the end of the day becomes pipe and a fan, as long as you've done all of the stuff we've talked about. You've conducted your building evaluation. You've gone through all of those options. You've done your diagnostic testing. You've determined your radius of influence. You know what type of fan you have to use because you know what type of resistance is under the building that you have to overcome. This, quite frankly, then becomes the easy part, which is installing the final solution. Once you've done that, we're going to go back in and we're going to clear the building. So the standard that we're going to clear to is MAMF 2017, and there's a January or recent revision. And that again is 100% ground contact. We want to make sure that when we're finished, we have not created any exposure concerns for other occupants in the building. And then we have to maintain. So there are 4 components or 5 components to the Omnm. Quarterly inspection. What we're looking at on a quarterly basis is just the operating pressure of the fans on those monitors to make sure that they're operating and they're operating within the performance benchmark that we set. Annually, we're inspecting the mechanical components of the system. Any routine or non-routine maintenance that needs to be done really falls into that. And then every 2 years, we're testing the impacted locations in the building just to verify that radon concentrations remain in those areas below the action level. And then every 5th year, or one time every 5 years, this is typically done in the 4th year to eliminate immobilization. You're actually recharacterizing the property. This table here, again, it's here for reference, and that expands a lot of what we've talked about with the Omnm program. So those are what would be happening after we complete construction. We've now confirmed that the construction was successful, occupant exposure has been mitigated, and we have a long-term stewardship plan in place to make sure that the systems function correctly and radon concentrations remain below the action level. As far as costing, slide from last time, single family average cost range for mitigation is $1,500 to $3,000 per unit. When you get up into this area, you're typically talking about crawl space areas where you're putting vapor retarders and things like that. And then on the multifamily side, the average cost to do the entire process is going to average somewhere between $2,500 to $4,000 per unit. And again, this was off of information that was provided upon request to HUD some years ago. I believe it was 2018. And I'll leave. I've got just a couple more minutes before I turn it over to Justin. And just to give you an example of costing, I know economics are sensitive everywhere, but you know, particularly within public housing. So here's just an example of that short-term versus long-term. So in this example, we have contractor A who didn't do any of the things that we talked about. It's not uncommon to contact someone and they'll give you a price right over the telephone to mitigate a multifamily building. So in this instance, there was some testing that was done to further help understand what needed to be done from a mitigation standpoint. This contractor did a pilot test, did the building evaluation and everything that we walked through. Contractor A put in 26 systems because there were 26 locations that were high. The system cost was a little less, and that resulted in this number. Whereas contractor B put in 10 less systems, and the system cost was higher because of the design and the fan performance. So 10 less systems, but it still ended up being about the same. The post-mitigation, and then the Omnm program plan. So the initial cost of installation on this project was about $14,000, almost $15,000 more between contractor A and contractor B. However, when you look at the overall cost or the long-term stewardship cost, this was off of a 35-year assumption for building life cycle and on the mortgage side. So when you're doing that Omnm with your 2-year, your 5-year, your $550 average routine and non-routine maintenance per 5-year for system maintenance, and then around $170 per year for electrical consumption, conditioned air leakage and whatnot. What you end up with is your long-term cost of ownership because of the difference in the number of systems and the approach that was taken ends up being, you know, almost $100,000, a little under $100,000 less. And so you end up with, within 5 years, you've recouped 100% of the installation cost with a $92,000 ownership costing advantage by doing a little more legwork on the front end. And with that, I will turn it back over to Justin, who is going to facilitate questions.
Hi, yeah, thanks, Kyle. And so a couple just housekeeping again. One of the questions was, will we get the slides? And yes, we'll share the slides with all of the anyone who registered. And then we are building a sort of unified Radon webpage. And so this recording and other webinars and guidance are going to go there. And we don't have that up and running yet, but we'll let people know when that's ready. And that's where some of this guidance is going to go. In the chat, I put a few sort of basic things on if you have really specific questions on a property or situation. There's a Kansas State, there's a hotline and a SOS Radon website. Put in a couple other links on how to find a qualified professional. And then also some links to the standards that both of the panelists talked about. So I'm going to try to do a few of the questions. Some of them have been answered in the Q&A already, and it looks like some are still being added. So I'll try to take a peek at what those are. And if we don't get to all of them, I think the plan is to have those posted as well when we post the webinar. So let's see, there was a question that came in actually via the chat, but it's an interesting one. And it was basically testing procedures when you have houses that have cross ventilation and no AC. And this was mentioned as a very typical construction in Puerto Rico and the Virgin Islands. So if the panelists have thoughts on that.
Go ahead, Dave.
Yeah, just to make a point, I mean, if you're in a, you know, somewhat tropical climate, and so your interior air tends to be the same as your exterior air, and there's no real connection to soil gas, then there's not likely to be a radon issue in that type of home. Especially, I think the question suggested that maybe it was pure construction so that it doesn't even connect down to the soil. So in that case, you living in paradise, you don't have a radon problem.
Yeah, and I would just add, we have a lot of experience in Puerto Rico. So a couple things there. You have the Miami style or the louvered windows, which you're going to do long-term testing in Puerto Rico. You're not going to be able to maintain closed building conditions in most instances. And the other is the building construction. You have concrete, hurricane-proof type buildings. And so I would agree with Dave. We're not really looking at soil-based radon in areas like Puerto Rico. If you do get a hit for radon, most likely it's going to be from the concrete building material. We've got a couple, 3,000-4,000 data points in Puerto Rico, and we've never run across a concrete emanation issue in that territory as of yet.
Great. So there were also a couple questions that came in, and I know this could probably be its own topic, but sort of the synergism and connections with smoking, and how can you tell if something is caused by smoking versus radon? And so I know that's a big topic of its own, but there were just a couple questions on that.
Yeah, I guess, we know from epidemiological studies that the risks associated with smoking and the risk associated with radon exposure are not just additive, but they're actually multiplicative, meaning that if you're a smoker and you're in a high radon environment, you have much higher risks associated with that. We're not quite yet at the point where we can identify specifically that a cancer was caused by radon exposure. And so no one ever really gets a toe tag that say they die from radon, but epidemiologically, if you rule out all other causes and there is a radon issue, then that's what's attributed as causal to a cancer.
Thank you. So let's see. There were a couple questions on sort of recommendations for retesting, and I think you sort of covered this, but if I could follow the question, I think it might have had to do with when you are doing retesting, should you do units that were not initially tested? And so maybe you could try to answer that.
Yeah, sure. So part of the ongoing maintenance and monitoring, yeah, that falls under monitoring. So the buildings would have been fully characterized on the front end. There was a problem that was identified. The problem was mitigated. Now, what are the testing recommendations in moving forward? Every 2 years, the recommendation is to retest the units that had a problem. And then every 5 years, to retest the property to determine that there are no other problems that have been created through preferential pathways opening that didn't exist, so on and so forth.
Great. So there's another question, and this might have been one from Dave's slides, but there were different like type of tests that were shown. And I think a lot of the audience are HUD grantees. And so they kind of function as property managers. And you might have gotten over this, but if they're sort of property managers of rental housing and they're going to be working with a qualified radon professional, is there an expectation what testing devices and short-term versus long-term they'll do?
Yeah, I think most likely you're going to be seeing short-term devices unless you have the special situations such as Kyle mentioned there. But again, depending upon the number of units and you're most likely to see laboratory analyzed devices, short-term devices. So liquid scintillation, activated charcoal, either in a tea bag or a charcoal canister.
Great. Another one, I think this is also for Dave, but the half-life concept, and actually this was my question, so maybe others had it too, but were you trying to sort of explain that even though, 12 atoms goes to 6 to 3, but the idea is that it's coming from the soil. So so it's still going to like replace itself. Is that what you were kind of trying to explain with the half-life?
Yes, I mean, I was trying to explain the concept of radioactivity, okay, in terms of half-life, but that was in a sealed box where no atoms could get in and no atoms could get out. We don't build houses like that. And so, yes, the connection to the soil and the preferential pathway and the source, which is radium, will continue to replenish that radon in a structure.
Great. So there were a couple, and I think one of you touched upon this, but there were a couple questions about utility costs for the mitigation systems. And I think one of you gave averages.
Yeah, that was Kyle.
Yeah, so there's the typical utility cost on a system. These are 1.5 amps type blowers. Sometimes you can get up to 4.5. And what you're looking at is $5 to $8 to $10 per month for that type of configuration. You do have some air leakage and different calculations, and I think we came up with about $170 a year per system to factor in for that. So if I were to put an average operational cost and pull that all together, I'd plan on somewhere between $200 to $250 per year per mitigation system for ongoing operation.
Thank you. So yeah, I think that kind of concludes sort of the grouped questions, and big thanks to Kyle and Dave for a really informative presentation, and for the participants with us. There will be a webinar number 3, and so stay tuned.
Okay, thank you, folks.
Thank you.
Yeah, hi, this is Peter Ashley. Just wanted to mention one thing that I forgot to mention is that we're going to issue an opportunity, and I mentioned that in the first webinar, for public housing agencies for radon testing and mitigation. I just wanted to mention it again. We'll be making $4 million available, and we will, of course, get the word out when that is published. But I just wanted to remind the audience that that will be going out. Probably it's going to take a while. I'd say a couple more months before that's published.
Yeah. Great. And yeah, that's a radon demonstration grant, and it's for targeted for public housing authorities for testing and mitigation. And so, yeah, that'll be being put out as a notice of funding soon.
Yep. And then just one other thing, Justin, I mentioned the third webinar is coming up. And I forgot to mention that Dave Kay is also going to be speaking in that, and he'll be talking about radon resistant new construction. It's always it's cheaper to build it in to new construction than to go after the fact and test and then try to mitigate. So maybe a lot of you aren't doing new construction, but it's good. It's a good topic to become familiar with in case you do in the future. So thank you.
Great. And that's July 27th. So thanks, everyone.